Hello everyone. Today we are back to the second talk of our ongoing series, What is, where we try to introduce interesting topics to 1 hour talks. Today we have Bikram Halder from BMAN third year. His interests lie in probability theory, and today here he is here to talk about Graphons. So, Bikram, whenever.
Yeah. Thank you, Dipto, for introducing me. So, before starting to look at what is Graphon, let's start with this question. अरे हाँ मैं लिखा लेजर কাজ করছে এই পয়েন্টার কাজ করছে না পয়েন্টার কাজ করছে না 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 এটা ওটার দোষ না রিফ্রেশ কর রিফ্রেশ So let's start with this question. Can we minimize this rationals? Uh, of course we can't because the minimum occurs at square root 2 by 3, which is irrational. But as we did, we used to approximate using some rationals uh, the number. So just like so, as we don't have solution to many problems in our rationals, and we had to extend our system to rationals. We looked at, so just like this, we looked at some other number system, namely rationals, uh, to deal with the problems. So let's look at some other question in graph theory. Can we minimize the number of force cycles of a graph among all the n-vertex graphs with edge density at least 10? So what do you mean by edge density? Let's introduce this and then I will come back to this question. So we define first a graph homomorphism. What is a graph homomorphism? It's basically a map from the vertex set of uh, map between vertex set of two graphs. Say we have graphs H and G, then a map from vertex set of H to vertex set of G becomes a homomorphism if it preserves the adjacency relation. Namely, if UV is an edge in H, then phi U and phi V must be an edge in G. We collect all the homomorphisms from H to G and call it hom H comma G and take its cardinality to small hom H comma G. Let's look at some examples. What about this homomorphisms from a point to graph, a whole graph? How many homomorphisms are there? So yeah, number of vertices. To a graph. No? Basically, what you are doing, you are mapping every edge to every other edge in G in two orientations. So that's why it's 2 times the number of edges. What about this number of homomorphisms from a triangle to a graph? So 6 times the number. Let's look at a different thing. What about the number of homomorphisms from a graph to triangles? Yeah, number of proper equivalents. Perfect. And for two graphs H and G, we define the homomorphism density to be the ratio of all the homomorphisms from H to G and all the maps from vertex set of H to vertex set of G. Basically, in other words, probability of choosing a uniform random mapping from the vertex of H to vertex of G such that it becomes a graph homomorphism. And we define the subgraph density, also known as the injective homomorphism density, to be all the injective maps from H to G divided by maximum number of copies that you can embed, uh, maximum number of copies of H that you can embed in G. Basically, you take all the copies that you can embed from H to G, and you take and in denominator you take maximum number of copies that you can embed in G. Right. So then, what the edge density becomes is basically two times the number of edges, just like we saw. Two times the number of edges divided by n times n minus 1 if it's n vertex graph. You are embedding in an n vertex graph. And the homomorphism density becomes two times the number of edges divided by n square. So as you can see, asymptotically these two are almost same. And indeed, their difference, if the vertex set of G is very large, their difference is, I mean, almost negligible. So asymptotic, we use these two things, subgraph density and homomorphism density, interchangeably as long as we have the graph to be large enough. Which one? This one. This one. This is the homomorphism density of edge. One edge. Yeah, K2 teacher. This one. Right. Back to our previous question. Can we minimize the four cycle density in a graph with edge density at least one? The theorem of Ardosh tells that the four cycle density is at least the fourth power of edge density of the graph. Now, if the edge density is at least half, then the four cycle density becomes at least 1 over 16. But can we achieve this minimum? Is it possible? It is shown that there is no finite graph that achieves such a minimum. But as we saw in our minimization problem in polynomial, uh, we approximated the number square root 2 by 3 with some rationals. So is it possible to approximate such thing with a sequence of graphs? Answer is yes. And uh, as you can see, say we take a sequence of random graphs on n vertices with edge probability. I mean, you decide each edges with probability half. You want to include or not, and you take everything you take independently, and you throw away all those all those graphs which is edge density less than half. Then can be shown that the four cycle density goes to 1 over 16 almost surely. But we showed that the density goes to 1 over 16. What about the limit of the sequence? How can we get any guesses? What about the limit of the sequence? Answer comes out to be a graphon. What is a graphon? A graphon is basically a symmetric measurable function from the 0, 1 square to 0, 1. Uh, now, as this is just a like, function on a 0, 1 square, but our graph is very discrete thing. How to uh, how to compare these two things? A discrete graph and a graphon. How to convert a graph to graphon here? How to deal with the question? How to deal with the question? Basically, what we do, we take the adjacency matrix of a graph. Say these are our half graphs where two edges are adjacent. Uh, where if you have two such partition, it is a bipartite graph. If you have two such partition V1 to Vn and W1 to Vn, you include Vi and Wj if I is less than or equal to j. So, for example, H6, you have a graph like this, and you write its adjacency matrix. And on the 0, 1 square, you divide you divide the 0, 1 square into boxes and put 0 and 1 into individual boxes. and then define the graphon to be functions to be that 0 1 function there. Then if we consider this sequence like this, then you can see that they converge to some sort of this kind of function, that wxy is 1 if x plus y is less than or equal to half, or x plus y is greater than or equal to square, and 0 otherwise. So this is sort of representing a graph into a function sense, and we took the limit. We saw saw this pixel image thing that converges to some function. Now let's look at some other example. Say you have a Ardeshini graph. Then your adjacency matrix, the entries of the adjacency matrix would be random with probability p. Fine, and it can be shown that the graphon, uh, the sequence of graphons related to this actually goes to a constant graphon, which has probability pair, whose value is p everywhere. Let's look at some other example. A checkerboard. This is basically a complete bipartite graph, and you label the edges accordingly and get this graphon. But where does it converge to? If we relabel the vertices, the graphon becomes this. So what should be the final? We took in the two partition here. We took odd numbers in one partition, even numbers in other partition, and here we took we level accordingly 1, 2, 3, 4, 5, 6, 7, 8. And not and for every complete bitarate graph, if we label using like this, that you take 1 to n in one partition and n plus 1 to 2 in other partition, then the graphon would look like this, constant graphon only, this one. So in our usual sense, this one only, because for every bipartite graph, the graphon is same, this graphon at least. Then what's the problem with this? Let's look at this. I will tell you what will happen later. So actually, what does it mean to converge this image to here? So we can relabel it actually. Actually we need to take best possible relabeling. So yeah, we need to make sense of what is best possible relabeling. So what do we mean by that? We need to deal with this question at the end of the talk. We will get it. So let's just like in the we defined homomorphism density uh, here in graph. Uh, we define the homomorphism density into a graphon also. We extend it. So say you have a triangle, then the homomorphism density should capture all the adjacency relations of the triangle in the graphon. So what should it be? Just basically, if you have edges like x, y, 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 z, z, x, it should capture the density and take the whole density. So it should be like this. So we define the homomorphism density uh, to be all the products of w x u x d, where uv are edges in H, and take the integration over over the VH dimensional field. Then this is for graphon, and we defined homomorphism density for graphs also. So are these two notions compatible? Turns out that yes, they two actually agree. This is a finite graph. This is a graph. W is a graph. Sorry, W is a graphon. We are defining the homomorphism density of a graph into a graph. So does that two yeah, they two agree, and you can check that. Basically, in the product, we are capturing all the adjacency relations and we are taking the whole density. Right. Now, uh, we want to talk about convergence. So we have a function here. We say that a sequence of graphs or maybe graphons converges if for every graph H. I mean, this H should vary on every graph. Every graph H, the corresponding homomorphism densities converge. And if such a sequence converges, what does the limiting object look like? You need to characterize it. So that's what our goal is. And if and are the two notions of convergence that this image and this graphon convergence, are they compatible somehow? You need to look at this. So we define another thing called cut norm. Basically, what is this? You take you integrate the graphon and you over all the measurable pairs and take the supremum. Uh, and you can check that this is a norm, but with identification, the W is almost everywhere zero. I mean, that means we are in zero. So, and as we have cut norm, we can define distance. Basically, what we do, we take infimum over norm, the distance between two graph on W and U to be infimum over all the possible, uh, over all the possible W phi and U phi, where W phi, you can think of it as W phi, 5x, 5y. This basically, you can think of it as a relabeling uh, of the graphon in, in our graph sense. So while taking the infimum, you're taking the best possible one. Here comes the answer to the question. Why should we take uh, why should we take this one and not this? Because this is the best possibility. Right? And you can see that the distance between this function and this function, I mean, of course, greater than the distance between this function and this function itself. So we need to take the best possible one. And here phi and psi are all the major Pisagni that's actually gives us the distance, gives us the real level. Sorry, what? Phi and psi are some major Pisagni. In the example, this is basically relabeling. You can think. So here it is identity, not here. Meaning, yeah, we just permute it. We just permute the vertices. So in our discrete sense, we are permuting, and in our continuous sense, we are just giving a measure to the unit. Measure to the unit is basically uh, what is transitive graph. So, so we have distance between two graphs. Now, can we define distance between two graphs? Is it possible? Check the corresponding graphs. Similarly, we can define distance between a graph and graph. Just take the corresponding graph and take the graph. Now, with this distance, now we have a distance here and a notion of convergence here. Are these two compatible? So, in 2008, these 5 people showed that actually yes, if a sequence of graph density sense, So if a sequence of graphons or graphs converges in our density sense, that T, then it converges also in our distance, where of course we identify two graphons to be, I mean, if they are almost everywhere same, and it is a Cauchy sequence under the cut distance. The three are equivalent, they show, and also that every convergent sequence of graphon has a cut distance limit. So you get closure, you got equivalence of convergence here. And if we take the set of graphons, and of course, as we mentioned earlier, if we identify two graphons, if they have cut distance 0, then quotienting it with that identification gives rise to a compact metric space. We already got completeness here. We already got completeness here. Just we need to show the totally bounded list. Then two graphons might be different, but their cut distance might be 0. Say if you have Dirichlet function and 0, then their cut distance will be 0. And these results actually actually are used heavily in various fields like large deviation, branching process, and animation. For large deviation, I can mention that 2011 paper by Saurabh Chatterjee and Varadhan, where they solved the problem of computing the large deviation of a triangle count in a rotationary random graph using Graphon. Or it is also connection to branching processes. Say you have a complete graph on n vertices, and you sample ui to un uniformly from 0, 1, and you take uh, and now you consider, sorry, you take the edge words uniformly from 0, 1, and you consider the minimum weight tree of the kn. It actually the sum of the minimum total minimum weight actually converges to April's function, that is beta 3. This shown. And recently in October 2023, so two people uh, considered this for general graphs. They took all the edges from uniformly from 0, 1, and then looked at the minimum spanning tree. And it can be shown that this minimum spanning tree actually can be expressed in terms of some branching process that is related to some inhomogeneous random graph. And also it has also application in random matrices. Say you uniformly sample ui to un from 0, 1, and you take a graph on w, Lifshitz graph on. Need to be Lifshitz, and you take the corresponding w ui uj to be your ijth entry in the matrix. Then it is shown that the fluctuation of the eigenvalue of this matrix actually converges to a weighted chi-square distribution or a normal distribution. This, what for any? Yeah, any Lifshitz graph. And also the, yeah. So this is a work in January 2024, very recent. Weighted chi-square or normal. So these are the references that I used here. This is basically the main paper, and this is that Chatterjee Vardhan's paper where they solved the triangle count large deviation. And this is the Lovash who actually pioneered the field. And the last one is Zhao's graph theory and combinatories, from where I made the slides. Yeah, I will add it. I forgot to add it here. So this is all I wanted to say. Thank you.
Thank you, Bikram, for the wonderful talk. Does anybody have any more questions for him? You take this and ask.
Oh, yeah. Thanks for reminding. Yeah. What is the graphon here, right? It is the trivial half. The trivial half. that works. Actually. So yeah, yeah, it is trivial half. Trivial half works. I mean, you can take almost really equal something else. Yeah, it works. So if you see the half here, put half 4 times here, and integrate, and you get 1/16.
Since we know that when we have a graphon, we have a sequence of tasks input that we have
Yeah,
graphon. So
compact matrix space. So you have a Bose-Einstein property.
any more
Any more
questions? Yes. Okay, since they're using the exact 3 million scale, so scale forward from graph 3 million scale forward is
for all graphs H? Yeah,
graph.
yeah.
So, like, is there any specific scale forward is what
Okay. Mm, I'm not sure about that. Hey, weak convergence is in probability. Weak convergence means you are in probability, but yeah. Ah, right. This is also one sort of averaging. So I think yes, yeah, some kind of averaging. So yeah, I think yeah,
the question was whether this is can be generated as an expectation in some proteins.
yeah, I guess yes, it can be. Maybe it can be. So this is basically the probabilities that you are integrating over, and yeah, I think it can be. Going to see it. So okay, any more question?
So if there are no more questions, we'll thank the speaker again. Thank you. Also, continuing this series, we'll be back next week when we'll have overall also we have a little bit more question. So I hope you all will tune in for the same. Thank you.